into YouTube right away. So I hope the weekend is long enough for some of you to study a little bit and also to absorb the material from last week, because there's quite a bit of material. I mean, this is going to be a pretty fast-paced class, so it's really super important to kind of keep up with the class and use the weekend to study a little bit. Basically, when I say study, it's really just kind of go over the concepts and see if you fully understand the concepts. And it's not really just reading the text and try to memorize everything. That's not going to help. All right. So we got about 3 more minutes before we are going to start. The YouTube recording has started already, so any questions that is asked from here on, will be logged in both in YouTube. And what we're going to do today is to finish up carry look ahead for binary addition, and then we're going to move on to binary subtraction today. The only question is, are we going to be able to finish binary subtraction today, or whether we'll need one more day, maybe tomorrow, to deal with binary subtraction. And then we're going to move on to signed value representation. I'm just looking at the sequence that is on the Canvas site. And then after we know how to represent negative values, then we'll talk about binary number comparison, because the mechanism to compare signed versus unsigned numbers is identical and also at the same time a little bit different. I know that sounds really confusing, but when we get there, we'll find out why I said that. Today we have a new lab. It is the 3x3 carry look ahead adder part 1. So that means there will be a part 2, which means at the end of part 1 you probably want to save your file just to make sure that you can access it in part 2. Alright, so I'm not seeing any questions on the text channel, so that means everybody is, well, at least everybody who has been listening is okay so far. I just want to kind of be a little bit naggy and just let the class know that it is really important to put an entry into the daily log, since for those of you who are doing this live, you might as well just do it now, because we got like about another minute before we have to before we start the class. So it's time to go to your daily log, open it up, just put in today's date, and use it to log the start time of important topics. So that way you have your own little catalog of what date and also what time on that date I start on specific topics. So that's going to be important. Other than that, I'm not seeing any questions yet. And oh, I just got a confirmation that the permission number seems to be working. Okay, I got some people responding that they got the permission number today and it is working. So there should be, everybody should have a permission number now in the class, because I sent the last few permission numbers to the last few people who were waiting to get into the class. So you might want to check your Gmail to make sure that you got your permission number. And then we got 10 seconds before we're going to start. So, all right. And it's time. Okay, so let's go ahead and get started. And I'm going to go back to this particular section in binary addition, where the real discussion of carry look ahead is located. So we'll look at several key pieces of this particular note here. The first big piece is this one here. Okay, there's a lot of okay, so to answer Catherine's question, I just added a daily log for you because everybody else already has a daily log. You are one of the very few people who is outside of a waitlist, so you should have a daily log created now, which is daily log dash 51. I'm just, oh, not yet, huh? Okay. I'm gonna have to, oh, okay, I think I know why it's not doing that. Just give me a second here so I can, or maybe I can fix it after class. That's fine too. Yeah, I think. Sorry? Okay. All right, gotcha. Yeah, I am just running the script on the side, and okay, now it's running. It will take a few minutes before it finishes its work. So let's get back to here. So this particular derivation, has a lot of Boolean algebra in it. But what is really important in this class, because this is not CISP 440, so I'm not really particularly wanting you guys to be able to do the derivations. So what we're doing is we are equating ki plus 1 to this little kind of messy thing here. So you might argue that this is actually messier compared to the original thing over here. And it doesn't even solve the problem, because the problem is ki plus 1. In order to calculate ki plus 1, we need to rely on k of I, and this is why we have a carry ripple effect, because you have to compute k of I, okay, and then you can compute k of I plus 1. And Edward, you might want to turn off your mic because I can hear stuff happening in the background. Thank you. Okay, thank you. So it doesn't seem to help. But what we're going to do next is we are defining g of I to be the conjunction of xi, yi, and we're defining p of I to be the disjunction of xi, yi. That doesn't seem to help too much, because all it does is to simplify k of I plus 1 is now g of I, or p of I and k of I. So the dependency of ki plus 1 on k of I seems to still be there. So next, what we did was we first look at what if I is 0. Okay, if we plug in I is 0 over here, then we can define k of 1 in terms of some g and p terms, and k of 0. Okay, so that part is not really surprising. And in this case, it's not really surprising that k of 1 depends on k of 0, because after all, k of 0 is part of the input, so it wouldn't surprise us that the result of an addition depends on the input. But then what we do is we work on what if I equals to 1. If we plug in I equals to 1 in this equation, then we end up with this, which doesn't seem to solve the problem that we have, which is k of 2 depends on k of 1. But now that we know what is k of 1, which is this little formula over here, or that expression over there, we can now substitute, instead of specifying that as k of 1, we now expand it to what k of 1 really is. And then we use distribution. Now don't forget to use distribution, because what distribution helps us to do is to reduce the number of levels of gates. Because if we do it this way, then we have to compute the OR, and then the result of the OR is going to be ANDed with P of 1, and then the result of that conjunction is then ORed with G of 1. So we have one additional level of gates. So after we perform the distribution, then we can see that we have 3 terms for the disjunction, and then each term of the disjunction can be as simple as just a G term, or it can be a conjunction between the P, G, or and also K0 term. So this basically fixed the number of levels of gates that we need in order to compute K of 2. So once we know the K of 2, using the carry look-ahead formula, which is this one here, then we can use that to substitute K of 2 when we try to figure out what is K of 3. So we, once again, instead of K of 2, we substitute the entire expression in place of K of 2, and then we do the expansion or distribution, and we end up with K of 3 being this mess over here. So as you go, you can see that there is a particular pattern to it. And whenever we see a pattern, after all, programming is all about noticing a pattern, and it is all about turning that pattern, using that pattern, and create algorithms so that we can solve problems. So once we observe that there's a particular pattern, then we make a general expression like this. Now I know this looks really messy, okay, but then I'll explain, how how to understand it so it doesn't look too messy anymore. So the idea of this particular equation is you can give me n of any non-negative integer, including 0, okay, and I'll be able to express k of n plus 1 in terms of a whole bunch of p's and g's and k0, but it would not rely on k of n. Okay, so this is the general equation to figure out a carry bit, but using the carry look ahead mechanism. So there were a few people asking, what exactly does this mean, and so on. Okay, so if this is the first time you see something like this, you can kind of look at this v notation over here as sigma. So basically, we are using it's a really big. It expands to a really big disjunction, whereas each term of the disjunction is determined by the index, which is I in this case. So you can see that each term that we use for this particular disjunction also depends on this little kind of messy conjunction over here. But it's the same thing. This is a conjunction of a whole bunch of p terms. Okay, but which p term we are putting into this conjunction is determined by the range of value that j is going to get. So j is going to go from I plus 1 to n. So within that quote-unquote loop, all of the p terms will be included in this conjunction, and then the result of this conjunction is then ended with g of I, where I is controlled by the outer loop over here. This is a whole different loop. It has nothing to do with the previous loop. So k of 0 is just here, and then we have a conjunction of pi terms where I goes from 0 to n. So do we have any questions about how to interpret this, or does anyone want me to kind of show the kind of C++ code version of something that looks like this? Because I can certainly kind of equate that expression to a loop construct that we already understand. So I'm just waiting a little bit here. If everybody is okay, I will just go ahead and move forward. And it looks like someone is using the 0611 text channel. Okay, that's not the important one. Okay. I'm not seeing anything here. Okay, so that means I'm not gonna use a loop to kind of illustrate what this whole thing means. All right. All right. So, oh, okay, somebody is writing. I'm gonna wait a little bit. Okay, I thought there was. Okay, all right. So I thought there was a question, and there was not a question. Okay, so what we'll do now is we are moving on. Okay, we are basically done with the discussion of binary addition. So the key point, okay, when you look at, you kind of have to zoom out sometimes. Okay, and I can tell you what I mean by that. So these equations, each line of the derivation is kind of analogous to pine needles. Okay, that's a lot of details to track, and it is important for you to kind of track all those details to be able to do it when you get to CISP440. But as far as we are concerned, that's really just kind of pine needles. It is not particularly important. But what is important about this entire chapter is there are two ways to perform binary addition. One is called carry ripple, which is what we did last Thursday. Okay, I showed you the circuit and I illustrated why it is called carry ripple, because the carry bit needs to ripple down the adder in order for each bit to be computed correctly. Okay, it's very simple and very elegant in design, but it's also kind of slow, because if you have a 64-bit adder, it's going to take 8 times, okay, 8 times as much time, 800% the amount of time of computing an 8-bit by 8-bit addition, because it depends on the number of bits. But So that's not good. And then the other mechanism, which is what this particular section 6, is all about, is called the carry look ahead mechanism, where we basically just use Boolean algebra and a few tricks so that we can now boil everything down to an expression that looks like this. What is the big deal? I mean, it seems like we just made everything more complicated. Well, the big deal about this is we have 3 levels of gate. Okay, now those 3 levels are not counting the AND gate for the G terms and the OR gates for the P terms. Okay, so not counting those that one single level of gates, we only need 3 levels of gate over here. The first level of gate is actually, I take it back, I lied. There are only 2 levels of gate. The first level of gates would be to compute all the conjunctions. So all of these conjunctions can occur at the same time, because they all have the inputs available already, so they can all occur at the same time. So after we perform all the conjunctions, then we take the results of all the ANDs to feed it into one gigantic OR gate. So that gigantic OR gate will take care of this OR as well as this OR over here. Because unlike infix notation, where we have fixed to saying, oh, this is an OR, it has 2 sides, we can only perform a OR on 2 values at the same time. Logic gates can take multiple inputs and perform a OR on all of the logic on all the inputs at the same time. So that's why sometimes when we express things in the infix notation, which is what we're used to, it doesn't really tell us how we can structure the expression when we are dealing with gates. All right, so do we have any questions about carry look ahead before we move on to binary subtraction? Because now would be a good time to ask any questions related to binary addition. All right, it looks like we do not have any questions about binary addition, so we're going to move on to binary subtraction now. So this is a student view. This should resemble what you should see. So we are basically done with binary addition, which is over here. Today's lab is 3x3 carry look ahead adder part 1, and this is what we are moving on to right now, which is binary subtraction. So now we are on binary subtraction. And there we go. So with binary subtraction, you can see each module may have a list of prerequisites. So the prerequisite of understanding how to subtract numbers in base 2 is how to add numbers in base 2. So what we'll do is we are going to think about the result and the borrow when we are performing a subtraction. And to do that, the best way is to use my journal. Okay, and I have been keeping the journal or the handwritten notes for this class. So let me just go ahead and start it up. Oh, it does know where to find something. Oh, okay. It doesn't remember where I last put that file, so I'm gonna search for that. And it's right here. Okay. And then we're gonna scroll to the last page, and we'll give it a new page 2. There we go. Page new after. All right, there we go. All right, so we're going to take a look at subtraction, and just like before, we're going to take a look at subtraction in base 10 first. In other words, we try to do something, well, at least I hope most people are familiar with. So the first question is, these are all in base 10, okay? So the first one is pretty easy, okay? What is 4 minus 1? Right? 3, okay? So we don't have a problem with this concept. And then we have, let's say, 4 minus 6, okay? This is all in base 10. So some people would say, oh, 4 minus 6 is -2, which is correct, okay? But you probably know that that's not the answer that I want, because I want an answer that will allow me to perform multi-digit addition. So the concept that will allow me to perform multi-digit addition is to say that 4 minus 6 is actually 8, okay? Well, but that doesn't seem to make any sense. Well, it does make sense in a certain way, because when you only have 4 candies and then somebody is asking you for 6 candies, okay, you can either tell that person and say that I don't have enough candies to give you 6 candies. But if giving the other person 6 candies is mandatory, okay, you have to do it, then we have to use the concept of a borrow. In other words, we have to find someone else and say, can I borrow 10 candies from you? Now, why borrow 10 and not 9 and not 11? Because 10 is the base that we're dealing with. So we are borrowing a 1 from the next digit. The next digit, which is the digit to the left of the one that we are currently concerned with, has a quantity that is 10 times the quantity of whatever column 4 minus 6 is dealing with. So when we borrow 1 from the next column, we're actually borrowing 10 times the quantity of whatever this column is dealing with. So the 4 is now becoming 14. 14 minus 6 is an 8. So in this case, we basically say the result of 4 minus 6, okay, I'm using the same notation here. So this time the order is important, okay, we are subtracting 6 from 4. So the result of subtracting 6 from 4 is 8. And then instead of C, which is carry, now we have a B, which is borrow. So the borrow of subtracting 6 from 4 is 1. Not -1, but 1. Okay, because we need to borrow 1 from the next digit. So you can probably see that, oh, we have another gigantic table here, especially in base 10. So in base 10, okay, you can kind of think about, a gigantic table here where this axis is x, this axis is y, and we just want to figure out, what is the result and what is the borrow for each one of these. So x goes from 0, 1, 2, 3, 4, and so on. Y goes from 0, 1, 2, 3, 4, and so on. And then for each cell, we have to figure out, okay, what is the result and what is the borrow. 0 is the easy one. It has no, the result is 0, and then the borrow is 0 as well. Okay, so what about 1 over here? This is going to be 1 minus 0. 1 minus 0 has a result of 1, but also a borrow of 0. Okay, so this row is pretty easy to work with because we are subtracting 0 from a particular value of whatever x is. The next row is a little bit trickier because now we are saying, what about 0 minus 1? Okay, 0 minus 1 has a result of 9 and a borrow of 1. Okay, 1 minus 1 has a result of 0 and also a borrow of 0. 2 minus 1 has a result of 1 and a borrow of 0, and so on. So this time, this table does not have any symmetry. In other words, if you draw a diagonal line down like this, the two sides of the diagonal line is not a mirror image of each other. Okay, because it's not addition. Addition is commutative, and that's why we only have to remember 1/2 of the entire table. But with subtraction, it is not commutative. So that's why this table is actually harder for kids to remember, because 4 minus 3 and 3 minus 4 are different. Okay, now some people can say, oh, but only the sign is different. Well, yes, but if I want to know, if I want to perform multi-digit subtraction, then it's a different table. Okay. So do we have any questions about the concept of subtraction, the result of a single-digit subtraction, and the borrow of a single-digit subtraction? Are there any questions about those concepts before we move on? Okay, I'm looking at the text channel and I do not see any questions, and I'm just double checking to make sure that my Discord is still running, because sometimes I don't see anything because my Discord has crashed. All right, so it looks like we do not have any questions. So without any questions, now we move on to binary subtraction. Okay, so in base 2, what are we dealing with here? Well, in base 2, we only have 4 possible cases. Okay. Oh, okay, we got one question from Martin. It's still confusing. Okay, so which part is confusing? The borrow bit, or okay, is it the borrow part that is confusing? Or general subtraction? I cannot tell which part is confusing. It'll be very helpful to me if I know which concept is confusing. All right. Okay. Borrowing. All right. So let's go ahead and perform an actual multi-digit subtraction in base 10. Okay. So let's just say that we have 406. Okay, and I want to subtract 100 and 108 from it. Okay, so this will exercise all of the options. Okay, so how do we do it? 6 minus 8 is 8 with a borrow of 1. Okay, I'm pretty sure this is what everybody has been taught to do. Okay, then we have 0 minus 0, which is 0. But then we have to subtract this borrow, because when we subtract 6, when we subtract 8 from 6, that column says, I don't have enough, 6 is not enough to give 8 to someone, so I need to borrow. And when it's borrowing, this column is borrowing a 1 from this column over here, and so that 1 is basically 10 times, okay, the value of this particular column. So the 6 becomes a 16. 16 minus 8 is 8. That is why we got an 8 over here. And then we have 0 minus 0, which is 0. And now we have 0 minus 1. So we got into the same situation now. Because if I have nothing and somebody asks me for 1, obviously I don't have anything to give to that other person. So instead of saying, sorry, I don't have anything to give you, I borrow one from the next digit, right? Now, this column is responsible for the number of tens, and this column is responsible for the number of hundreds. So when I borrow from the 100th column, it is equivalent to 10 times whatever quantity this column is dealing with. So the 0 now becomes a 10. Okay, this borrow here is making this digit looks like a 10. 10 minus 1, which is the borrow to the unit column, gives me a 9. So when I finally move on to the 100th column, we have 4 minus 1, which is 3, and then we have to subtract this 1 from the 3, because that one is already loaned out to the 10 column. So now we have a 2 over here. So is that okay? I mean, is everybody okay with this particular subtraction in base 10, which illustrates the concept of why we borrow? All right. So I'm assuming that we are good with this. All right. All right. So assuming this is good, now we move on to base 2. So in base 2, we have 4 scenarios, right? So we have 0 minus 0, which is easy. 0 minus 1. Also, the other way, 1 minus 0. And then we have 1 minus 1. And then the only one that is a little bit tricky is 0 minus 1. 0 minus 0 has a result of 0 and a borrow of 0 as well. Okay, we are kind of pretty easy on this. This one is easy. 1 minus 0, it's kind of easy too. The result is 1 and the borrow is 0. 1 minus 1, the result is a 0. The borrow is a 0 as well. So the first three cases hopefully is pretty easy because regardless of the base, okay, those three cases are pretty generic. The last one is the only one that's tricky. Okay, in base 2, when we subtract 1 from 0, the result is 1, and then the borrow is 1 as well. Because there's not enough in a 0 to give somebody 1. So now we have to borrow from the next column. But in base 2, the columns are doubling the values of the one to the right hand side. So when we borrow 1 from the column to the left, we are borrowing a quantity of 2. 2 minus 1, this 0 becomes 1 0 in base 2, which is 2 minus 1 is a 1. That's why the result is a 1. We need to borrow because there's not enough in 0 to give 1. And that's why we have a borrow of 1. So are there any questions about this particular thing over here? Let me highlight what I mean by this particular thing. So are there any questions about this portion? All right. So looks like there are no questions. All right. Martin's typing. I'm going to wait a little bit. Okay, absolutely. Okay, so this is great. So I'm going to call this X, and this is Y. Okay, there are very specific names in the subtraction. X is also known as the minuend, and then Y is also known as the subtrahend. But right now we just call it X and Y. Okay, so we got one column X, one column for I. They are independent Boolean variables or base 2 variables. So when X is 0, Y can be 0 or 1. When X is 1, Y can also be 0 or 1. So now we have 4 rows. We have the result, and then we have the borrow. 0 minus 0 has a result of 0. 0 minus 1 has a result of 1. 1 minus 0 has a result of 1. 1 minus 1 has a result of 0. 0 minus 0 does not need to borrow anything. 0 minus 1 needs to borrow. 1 minus 0 does not need to borrow. And then 1 minus 1 also does not need to borrow. So I just converted that into what seems to be a truth table. So now we are focusing on this little table here now. So now we're going to use the same trick that we did with addition. In other words, we're trying to look at this table and go like, I wonder, okay, because the result and the borrow of a subtraction is an arithmetic operation. But we don't want to perform arithmetic operations because all we can do with transistors are Boolean operations. So we want to translate everything into Boolean operations. So now we're asking the question, how are we going to do this? So we'll focus on one thing at a time, and just like everybody else, I'd like to do the easy stuff first. Okay, so June has a question, and then Bupinda has a question. Bupinda. There we go. So go ahead. All right, so June says, so we will need an exclusive OR gates since those are the only patterns I see. Okay, we also need negation, by the way. Negation is also important. Okay, and then Bupinda is typing. I'm gonna wait for that. Okay, it's the same thing like a half adder. Yes, it is a little bit like it. Okay, so we'll first identify things that we already have seen before. This column here, okay? Hey, we have seen this. This is identical to what we need to do with binary addition. And if you recognize that pattern, you are 100% correct. So we'll go ahead and make note of that, okay? In subtraction, r of xy is the same thing as the r of xy in addition. Okay, so there are two ways to do it. If you want to do it the easy way, you just use exclusive OR. But if you want to kind of expand it out to use only and or not operations, then we kind of have to do it the longer way, which is x and not y, or not x and y, okay, which is identical to the one that we have for addition. Okay, so that doesn't seem too bad. So now we look at the other one and go like, I wonder if we can borrow, the carry function in addition. And go like, no, unfortunately, it doesn't work this time, right? Because in addition, 1 plus 1 has a carry of 1, but in subtraction, 0 minus 1 has a borrow of 1. Darn it, doesn't work. So instead of just doing a conjunction, when you subtract y from x, the only time we need to borrow is when x is a 0 and y is a 1, right? Because that's, we're looking at this row over here. Oops, this row over here. So when x is a 0 and y is a 1, we want whatever expression we want to come up over here to be a 1. So the quickest and easiest way to do it is simply to say, well, since x is going to be a 0, then the negation of x is going to be a 1. And since y is going to be a 1, we don't need to negate it. So the conjunction between the negated x and the non-negated y is going to be the borrow function. Oh, so that's just a little bit different compared to the adder. All we had to do was to negate the x first, right? So I just want to make sure everybody is associating the r and the b function in subtraction to, they kind of like the r and the c function in addition, with the only exception that b is a little bit different. Otherwise, not too bad. All right. So to walk through the truth table for the borrow, okay, you can do this. So you can say xy 0 0 1 1 0 1 0 1, and then we have the borrow, which is not xy. Okay, now not xy is not x and y. So on the first row, since x is a 0, not x is going to be a 1, but y is a 0, so the whole thing boils down to a 0. On the second row, x is a 0, not x is a 1, y is also a 1, so we have 1 and 1, which is 1. On the third row, y is a 0, so we know the whole thing is going to be a 0. On the last row, x is a 1, so not x is going to be a 0, so the conjunction is going to be a 0. So we look at this column. Okay, so let me use yet another color to highlight this. Okay, so you can see how the green box looks exactly the same as the kind of purple box, and that's why we can use not xy to implement the borrow. All right, so there we go. Okay, wow. Okay, so this is kind of cool because all it means is now we can implement a half borrower, okay, if you will, because instead of having the carry bit, we just have the borrow bit. Okay, so they look almost identical, with the minor exception that instead of a straight up conjunction between xy in order to compute the carry, we first have to negate the x and then we perform the conjunction to compute the borrow. That's the only difference. So let's check out what we have in the notes. Okay, so in the notes here, we are basically done with section 4, which is identifying that the r function is the same as addition, but the b function is a little bit different. It is the negated x and y. Okay, so that's the only difference. Section 5 talks about borrow propagation or borrow ripple. So basically, we are implementing half borrowers and then full borrowers. But the architecture of those in terms of the connectivity between the half adder to make the full adder, in terms of the half borrower and the full half subtractor. I kept referring to the wrong term. The half subtractor and the full subtractor, they actually have exactly the same topology, the way they are interconnected, is exactly the same. The only difference is to compute the borrow, we first have to negate the x. Okay, so section 5 is fairly easy to implement. So if anyone wants me to kind of use what we had for the adder to implement the borrower, we can go ahead and do that. If not, we'll go ahead and just kind of go to section 6, which talks about the look ahead mechanism. Okay, Richard says, I'm assuming the yes please is to refer to implement the borrow ripper subtractor, which is analogous to the carry ripple adder. Okay, all right, so let's do that. Let me see if I still have that file. If not, it's easy enough to reconstruct it. All right, so here's Logisim. And I made it a little bit too long so you guys cannot see the bottom. Now we can see it. There we go. And let me see if I still have the adder. I might not have saved it, which is okay. We can just take a look. Yeah, I don't think I saved the adder circuit. So we'll just go ahead and reconstruct everything. So first we'll construct the half subtractor. So the half subtractor has x, which is also known as the minuend. It has got a y, which is also known as the subtrahend, as input. And then on the output side, it has got the result, okay, which is r. And it also has the borrow, which is our b. There we go. And now we have to kind of use the gates to compute each one of the output from the input. So this time I'm going to be just a little bit lazy and utilize exclusive OR instead of last time using a bunch of 2 AND gates and an OR gate to do it. So this time I'm just going to be a little bit lazy and use an OR gate. So the OR gate first has to change. We first have to change the number of inputs and then the size of the gate. Oh, wrong place to click. There we go. So this is going to compute the result, and to compute the borrow, we're going to need an AND gate. So once again, change the number of inputs to 2 and change the size to narrow like that. So now we have the borrow. But in order to compute the borrow, remember we have to negate x first. So that means, I can use this kind of nifty little trick here to negate the top input, but leaving the bottom input non-negated. So we just need to feed both of the inputs to the right input. Oops, nope, that still works. Okay, and then this one connects to here, and then Y connects to the other pin of each gate, like so. And then the output of each gate connects to the output, like that. Okay, so now we can test the circuit, see whether it works or not. 0 minus 0 has a result of 0 and a borrow of 0. Okay, looks good. 0 minus 1 has a result of 1 and a borrow of 1. Looks good. 1 minus 0 has a result of 1 and a borrow of 0. Looks good. And then 1 minus 1 has a result of 0 and a borrow of 0. So for all 4 possible cases, this circuit is working. Okay, so now we can say, let's turn it into a component. That's it, right? And then we just have to, this time we kind of have to label it carefully, because subtraction is not commutative. So we do have to clearly indicate which one is x and which one is y. And then we have the result and the borrow. And then we move these things into kind of the place that we want to put them. Here's x, here's y, and here's r, and here's b. There we go. And if you really want to clearly indicate what this gate is doing, or it's a half subtractor, we can just say x minus y, put it as a label over the entire chip over here. Okay, so this way it's kind of really super clear what this little gate is doing. Or if you say, but it's a half adder, okay, well, or half subtractor, then we can just change it to be a half subtractor. Okay, so we can say 1/2 of x minus y, which is a half subtractor. Okay, or you can say half over here. Whatever you do, it's fine. Okay, it's just documentation so that we can look at the packaging and know what the gate is supposed to do. All right. So now we go change the name of the circuit because it's definitely not main. Okay, it is a half subtractor. Half subtractor, like so. So the next thing we do is to implement a full subtractor. So we add a circuit, and we call this one full subtractor. So, and we already know how many half subtractors it's going to take to implement the full subtractor. Exactly 2. Okay, so here's 1, duplicated, and now we got 2. We also got 2 input pins, right? So we got 3 input pins. So we got the input pins are going to be a little bit messy because they don't truly align with the positioning of the pins on the chips. So I just have to move things around a little bit. So I'm going to call this one X, or using the previous terminology, this is Xi, this is Yi, which is bit I of Y and bit I of X, and this is going to be Ti, okay, which is kind of the borrow bit, but instead of using Bi, which is confusing because B is already used for the borrow function, I use T, which stands for take. Okay, so this is Ti, and we, just like with a full adder, we hook up X and Y into the first half subtractor as themselves. Okay, so the result of this, which we know as Q, goes to X over here, and then the Ti goes to the Y of the other half subtractor, like so. And then whatever's coming out of the R is the actual result, which is the difference. So we make an output pin for this. So after I draw this picture, we'll test it out a little bit, and then we're going to do some binary subtraction by hand. So that will further help people to understand what this is all doing. So now we got 2 B bits coming out. Okay, so now is a good time to go back to our example over here. Not even the base 2, just the base 10. So in the base 10 example, you can see how this one here, okay, is because of the 6 minus 8, but this one here is because of the result of the subtraction between X and Y minus the one the borrow from the previous column. So there are 2 ways to contribute to a borrow again. Okay, just like there are 2 ways to contribute to a carry with an adder. So going back to this circuit here, the way we combine these two, once again, is an OR gate. So we just pull a OR gate over here, fix its size, and I have no idea why the default is the big one with 5 inputs, because in reality, we don't really have a lot of formulae that require like 5 inputs to a gate. So there we go, we hook it up, and this new pin is going to be our Ti plus 1 pin, which is to the next digit, and all we need to do is to do an OR between the 2 B bits. So if you took notes, or if you kind of know where to go back to the video for the carry ripple adder, you probably recognize this picture, don't you? The only difference is, instead of half adders, now we have half subtractors. instead of labeling, ti, instead of using ki as a label, now it's ti. Instead of ki plus 1, it is now ti plus 1. That's it. The topology is the same. Okay, the way we hook up the wires is really actually the same. So Richard, does that kind of answer the question of how to make the full subtractor out of the half subtractors? Yep. All right. Excellent. And does everybody see how this really is resembling the topology, or how things are connected with a full adder? The way I hook up the half operators, and how the output, the B versus the C of the outputs, are ORed together. Yeah, we can work it out. Sure. But first, yeah, we'll work out the circuit first, and then we're going to work it out, as an example. All right, so let's now, make a real circuit. Okay, so now we'll go ahead and make a new circuit, which is a 3x3 subtractor. Okay, so 3x3 subtractor. So it's going to take up 3 subtractor circuits, and I'm going to use the same kind of layout as the other one. So, yep, I think that's how we staggered the full adders when we implemented the 3x3 adder. So this time we have X, which is the 3-bit input. Whoops, 3. Come on, give me 3. There we go. This is X, this is Y, and we also have the extra 1 input, which is our K0. But this time it's called T0. Okay, so T0 is over here. This is our X, and here's our Y. There we go. But these are all individual bits. Okay, when you look at these ports, they're all individual bits. So there's no way I can just hook up a wire over here. But you guys already know what to do with this, right? Because we just need a splitter to split up all the bits inside the 3-bit pin. So we have a 3-bit wide splitter that split to 3 ends, and we're gonna have 2 of those, one for X and one for Y. So this is the one for X, and here's the one for Y. Let me see if they still work. There we go. All right. So first thing first, T0 needs to go to the KI pin of a half subtractor. So this one goes over here, and then bit 0 of X goes to XI of the full subtractor, and Y0 would go to the Y pin of the half subtractor. Let me go back and change the caption, because now you cannot see which pin is which pin. So if I go back to the full subtractor and go to its appearance, now we can go ahead, I can go ahead and kind of give these names. So we got TI, XI, YI, and then we got TI plus 1, and also DI plus DI, which is the bit I of the difference. And then we just need to move these things around so they align with what they're supposed to be documenting, the pins they're supposed to be documenting. So here's XI, and here is YI, and then DI is here, and then TI plus 1, there's not enough space inside the chip, so I'll put it outside of the chip like that. And we'll go ahead and clearly indicate this is XI minus YI. This is a subtractor. So now we have, so this is the cool thing about Logisim, is you can retroactively go back and document a circuit's appearance And when you go to the circuit that makes use of it, it will all be in there too. So it's kind of cool. All right, so we have to take the output ti plus 1 to ti of the next full subtractor, and then di goes to its own output pin, so we'll hook up those later on. Now we need to take x bit 1 of x and hook it up to xi, and then we take bit 1 of y and hook it up to yi, and here's the last one. The output ti plus 1 goes to ti of bit 2, and x2 goes to xi of the last full subtractor, and bit 2 of y goes to yi of the full subtractor of bit 2. And now we have 4 pins, okay, 4 output pins that need to be connected. Here's 1, 2, 3, and 4. So the DIs would go to an output pin which is simply labeled D for difference, but it's a 3-bit output pin, which means we need a merger, which is the reverse of a splitter. So we just have to kind of flip, not flip, but change the facing, so it's now facing west. Now, when you flip something like this, it's also important to notice, which end is bit 0 and which end is bit 2, because we don't want to do a mirror image on those bits. And obviously, I picked the wrong pin because this is an input pin. So to flip an input pin to an output pin manually is doable. It's just a little bit of extra work. The facing is going to be west, and then the output is going to be a yes. So now it becomes an output pin. All right, so here's our output pin. We take bit 0 of we take the difference of bit 0 and hook it up to bit 0 over here. We take the difference bit of bit 1, hook it up to bit 1 over here, and then we take the difference of bit 2 and hook it up over here. And now we need 1 extra output pin, which is the overall borrow of the entire subtractor. We'll just call it B out, okay? And that's just a straight connection from ti plus 1 of bit 2 all the way out here. Okay, so now we got a 3-bit by 3-bit full subtractor. We'll go ahead and give it a try, okay? But before we do that, we want to do it by hand first, okay? So we'll go ahead and do some binary subtraction, multi-digit binary subtraction by hand first. So let's open up a new page, and then we'll do some subtraction over here. All right, so let's check out this particular subtraction. Let's see. Let's go ahead and try 0, 1, 0 minus 1, 0, 1. Okay, there we go. So this is in base 2. So we're going to set up the rows. Okay, this is row X, this is row Y, this is Q. Q has exactly the same meaning as in an adder, okay, because the equation to compute the Q's are the same. This is our row called T, which are basically where the borrow bits are, and this is row D, which is the difference instead of the sum in an adder. So this time I'm going to work this out in a very strange way. I'm going to work on this row by row, okay? So what do I mean by row by row? We'll finish the entire Q row first, because Q is the exclusive OR between the X and the Y, so we have 1, 1, 1 in this case, okay? What about the T row? Well, the T row is a little bit interesting because it looks kind of the same as the K row in an adder. This is usually assumed 0, okay, so we'll just leave it alone. Now, this one here, okay, let me just kind of change the color to something here. This one, there are 2 sources to contribute to this bit over here. it can be the borrow of this or the borrow of this. Okay, so both of these can contribute to this particular borrow bit. And we can see that at least one of these two, which is in this case the top one, is contributing the borrow. So now we have a borrow bit of 1 over here. And then over here, this particular bit, let me change to different color. So this particular borrow bit can be because of this subtraction, or it can be because of this subtraction over here. But in this case, neither is contributing a borrow, so that's why it ends up with just a 0 in this case. Now we can work on the D row. The D row is the exclusive OR between the Q and the T. So these two exclusive OR is a 1, these two exclusive OR is a 0, and then these two exclusive OR is a 1 again. Now I forgot one last thing, which is this overall borrow here. This can contribute this this particular bit here can be contributed by XY, the XY bits, or it can be contributed by the QT bits. Okay, but we can see that the XY bit is already contributing a 1 over here, so we have an overall borrow of 1. All right, so knowing this, let's go ahead and flip some inputs in the logic gate and see whether this is what we get in our circuit implementation. So we have 0 minus 0 minus 1 0 1, and let's go ahead and check it out. Okay, I cannot I can't show both at the same time unless I resize Logisim, which I can do. So let's go ahead and do that. So I'm just resizing Logisim so that we can fit Zerno as the bottom half of the screen, and scroll this up a little bit. There we go. So now we can actually see how to work this out. So T0 is basically this particular 0 here. So in most cases we just want a 0, but in some cases, like when we want to daisy chain 3-bit by 3-bit adders, then it'll be coming in from the borrow out of another subtractor. Okay, I thought somebody typed something on the text channel. So we are going to flip this middle bit here so that we have 0 1 0 as X, and then we'll flip both these two bits of Y so that we have 0 minus 0 minus 1 0 1, and the result, the difference, is 1 0 1, which is what we got here, and it has an overall borrow of 1, which is also what we got here. So is that answering the question, Murtaza? Alright, I'm not seeing any activity in the text channel, so I'm going to assume this is okay. Or do you guys need a little bit more time to absorb this? Okay? Okay, yes to what? Yes to needing more time, or yes to we got this? All right. So June is typing. Okay, I think we got it. Okay, so I think Murtaza is using the text channel for typing questions, but I'm suspecting Murtaza is using YouTube for watching the screen. So if possible, switch to Discord and use the Discord live stream to watch the screen, because there's a huge delay between my question and Murtaza's response, and I think that's because Murtaza is using YouTube instead of using Discord for the live streaming. All right. So now that we got this, we look at this picture and then we say, don't we have exactly the same problem now that with the same problem that we had when we were using carry ripple, except this is borrow ripple. What do I mean by borrow ripple? This borrow is needed to compute this borrow over here. This borrow is needed to compute this borrow over here, and that borrow in return is what is needed to compute the overall borrow. So that's this is the problem. Okay, it's exactly the same problem that we had before, which is in order to compute like a 64-bit subtraction, that's going to take 8 times the amount of time of an 8-bit by 8-bit subtraction, because the amount of time to compute a subtraction is linear to the number of bits in the subtraction. So that is kind of a problem, right? So I think I just want to go back to address Mertesa's comment. I'm suspecting that Mertesa is using the web-based client for watching the live stream, and I think that's why the live stream in Discord is not working. So Mertesa, when you have time, you need to download the Discord client specific to your operating system, and I know that Discord is available to Windows, Linux, and Mac OS X. So that's what you need to do, is to install the client that is native to the operating system that you're using. Then you will be able to watch the live stream through Discord. And that's going to improve the lag time, or it will reduce the lag time by a whole lot, because YouTube is just really, really slow when it comes to the lag time. All right, so we got that out of the way. So we have the same problem, which means we need some kind of a solution to deal with this. So getting back here, okay, so now we have this. Okay, first of all, we want to know whether this has to be an arithmetic addition or can it be a disjunction. Okay, it's the same argument that we had before. The only time that we cannot use a disjunction in place of an arithmetic addition is when both sides can be true at the same time. In other words, if this borrow and this borrow can be true at the same time, then we cannot replace this arithmetic addition, with a disjunction. But we really, really want to replace it with a disjunction. So now we have to do some analysis and ask, can both be ones? So we know that when this is a 1, x is a 0 and y is a 1, right? But when that is the case, what is the q bit? When xi is a 0 and yi is a 1, what is qi? Qi is computed exactly the same way as in an addition, which is the exclusive OR between xi, yi. Okay, I think I can hear what you guys are thinking, so I'm going to try to spell it out. Okay, when xi is a 0 and yi is a 1, okay, qi, which is the exclusive OR between xi, yi, is going to be a 1. Okay, so we know that when this side is a 1, then qi has got to be a 1 as well, because it's the exclusive OR between xi, yi. But when qi is a 1, then we know this entire borrow is going to be a 0. Now, it makes sense from two perspectives. It makes sense from the perspective of the Boolean expression that we use to compute borrow, which is negating qi and the non-negated ti. Since qi is a 1, not qi is going to be a 0, so the borrow is going to be a 0. So this is looking at it from the perspective of the Boolean expression that we use to implement the borrow. But it also makes sense from the perspective of arithmetics, right? Because these are both binary digits. If qi is a 1 already, there's nothing you can specify in Ti that is greater than Qi, because after all, in base 2, each digit can only be a 0 or 1. So if Qi is a 1 already, then we only have two possible scenarios. With the second, the Qi minus Ti scenario, you can have 1 minus 0, or you can have 1 of 1. Neither is going to have a borrow of 1. So we know that when this side is a 1, this side has got to be a 0. Okay? Now it works the other way too. When this side is a 1, we also guarantee that this side is going to be a 0. Why is that the case? Because when the right hand side is a 1, that means Qi has to be a 0. If Qi is a 0, that means the exclusive OR between x and y is going to be a 0, which means xi and yi have to be the same. But if xi and yi are the same, then the borrow of xi minus yi is also guaranteed to be a 0. So it works out in both ways, which also means we can now say that, oh, this plus here is a disjunction, because it will never happen that both sides of this plus are ones. Okay? So when you read this plus here is actually a OR. It is not an arithmetic addition. So then what we do is we have another huge long derivation. I think this one is slightly longer than the other one, but it uses kind of the same tricks. So I'm not gonna, work out all the details, because I just want you to focus on the end result of this derivation over here. So the end result of the derivation is I can now express ti plus 1 as not xi and yi, or not xi or yi, the whole thing, and ti. You look at this and go like, well, that didn't seem to help. So what we'll do next is we are redefining. Okay, note the RE is underlined because G and P's are defined slightly differently in a subtractor compared to an adder. Okay, the only difference is we negate x first. So G of I is no longer xi and yi. Now it is the negation of xi and yi. Pi, kind of the same thing. We first have to negate xi. So pi is now the negated xi and or yi, and not just xi or yi. But guess what? Once we define gi and pi this way, we end up with something that looks kind of familiar, right? Because now t of I plus 1 can be expressed as g of I or p of I and t of I. All right, cool. So if we just change all the k to t from the previous module, then everything will work now. In other words, this equation still applies, because all we are doing here is to replace all the terms that starts with the k to t. That's all we did. So the mechanism that allows us to use carry look ahead can also be applied when we perform subtraction. So now we have a borrow look ahead subtractor, and this is how we compute all the t bits. All right. So do we have any questions? Because this is kind of big, because it looks like in binary arithmetics, addition and subtraction are kind of the same thing. It's just a question of, are we negating x first? That's the only question. If we are dealing with subtraction. If we don't, we are dealing with addition. Now, isn't that cool? I'm just looking at the time here. We got 10 minutes. Do we have any questions about binary addition and binary subtraction? Does everybody notice how, the same mechanism that allowed us to perform carry look ahead in order to implement an efficient adder, it's exactly the same mechanism that allows us to design and implement a borrow look ahead subtractor. It's basically the same topology. The only difference here is we have to negate x first. Cool. All right. Thank you for the confirmation, Sakil. All right. So this is kind of cool. I mean, we're just kind of zooming along. So the next thing we're gonna do. Oh, okay. It timed out already. So the next thing we're gonna do is to talk about. Oh, okay. Yeah, I just have to leave student view. All right. So the next module down the list here. So we are now done with binary number addition. We are also done with binary number subtraction. The next module is signed value representation. In other words, so far, okay, with base conversion, we know how to convert positive integers or non-negative integers into base 2. No big deal, okay, the equation works just fine. So now the question is, what about negative values? In other words, if I have a negative value, how am I going to represent that negative values only using zeros and ones? So I'm looking at the time, we got about 8 minutes or so. So we are not going to be digging into a whole lot of details, but we can still kind of dig into some concept that we'll be using tomorrow in order to understand signed versus unsigned number representation. So what we'll do is I'm going to start a new page here because it is a kind of a new topic. So this is the sort of thing that I think it would be helpful to put into your daily log is, when I start to talk about signed representation, what date and what time on that day did I do that? Because this will let you locate the video or the recorded version of this video, this live stream on YouTube really quickly, so that if you need to go like, okay, I can't quite remember what text said about the number circle, now you know where to look, because this is exactly what we're going to do. It's a number circle. So instead of a number line, we're dealing with a number circle. Why is that the case? Well, it has to do with, in a computer, you can only allocate a fixed, usually, not always, but usually you're allocating a fixed number of bits to represent an integer. So before we move on to that particular discussion, I think it'll be very helpful to take a look at a few C programs, because we are familiar with C programs, hopefully. So now we can, I'll go to the temp folder and type a few, type one particular program, and we'll just call it ints. And the first thing we do is something that is probably not familiar to most of you, not at this point, is to pound include standard integer.h. This is not a typo. I did not intend stdio. This is actually stdint for standard integer.h is a header file. And we'll just go ahead and use a main function. Has a return statement here. And we're going to use some really kind of interesting stuff. This is unsigned 8-bit integer. We'll call this x. This is unsigned 16-bit integer. We'll call it y. This is unsigned 32-bit integer. We'll call it z. And this is unsigned 64-bit integer, and we'll call it w. And I need to do something here in order for the variables to continue to exist. So I'm gonna do a assignment so that all of them have an initialized value of 0, because this line is technically not needed, but I need it to be here because otherwise GCC is smart enough to optimize all the local variables out. Then I cannot illustrate what I wanted to illustrate. So here we go, and then we compile this code. There we go. And then we use GDB to kind of take a look at this program when it executes. Oh, I forgot to compile with -G, which includes the debug symbol table. So now we can actually look at the source code. And I'll put a breakpoint on line 11, run the program. Now the program has paused on line 11. Okay, the values of x, y, z, and w are not important, but the size of those things is. So if I say, what is the size of x? It says 1 byte. What is the size of y? 2 bytes. What is the size of z? 4 bytes. What is the size of w? I think you guys got the idea. 8 bytes, right? All right. So, that's interesting, because it seems like in most programming languages, when you say, okay, I need an integer, you kind of have an implicit length, or the width, I should say, width to the integer. We're only allocating a certain number of bits in order to represent integers. But this is also why, instead of a number line, we have a number circle, because what happens when you add 1 to the largest value of an unsigned 8-bit integer? It rolls over back to 0. Okay, I'm not going to use 8-bit or 16-bit over here. We'll just go ahead and use 3 bits. Okay, but we know that with 3 bits we have 8 distinct values, or 8 distinct bit patterns. Okay, the first one is 0, 0, 0. Then we have 0, 0, 1, 0, 1, 0, 1, 0, 0. Oops, 0, 1, 1. Okay, I skipped one over here. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1 over here. Okay, so these are all the bit patterns that we can represent, given that we only have 3 bits. So what is the big deal? Well, the big deal is, let's see what values they can represent. Okay, so these are the bit patterns, and I'm going to use blue to represent value that we want that particular bit pattern to represent. Oh, that's a no-brainer. This is representing 0. This is representing 1. Based on base conversion, this is going to be a 2. This is going to be a 3, 4, 5, 6, and 7. Okay, so if I have 3 bits, then without a whole lot of trouble, I can quite easily understand that we can only represent integer values from 0 to 7. Okay, that's pretty easy. Now we have to think, what about negative values? Well, it looks like, if I have a needle, okay, so let me see what is the best way to make that needle. I think I have to undo a whole lot to kind of repoint the needle. Okay, so if I have a needle like this, okay, and I want to add something, you can see that adding is rotating that indicator clockwise. If I want to subtract something, it's rotating that needle counterclockwise. Okay, this is for subtracting, and this is for adding. Actually, it's not the VE. This is for subtracting, and this is for addition, like that. Okay, it seems to make sense, right? So let's use an example. Let's say we want to add 3 to 2. Okay, so the pointer originally points to 2, and we want to rotate it basically 3 times clockwise. So here's 1, here's 2, and here's 3. So 2 plus 3 is 5. Oh wow, that it works out. Nice. Okay, what about subtraction? Well, let's say we are subtracting 4 from 6. Okay, so we start here, and subtraction is to rotate the pointer counterclockwise. So we have 1, 2, 3, 4. So after rotating counterclockwise 4 times, we got 2. 6 minus 4 is 2. Ah, that works out too. Very nice. So now the question is, what about -1? Well, -1 is not in this picture, but if I have to pick a slot, okay, pick a binary bit pattern to represent -1, where do you think it should go? -1 is 1 less than 0. So if I rotate that pointer counterclockwise once from the position of 0, whatever is there is the one that I want to use to represent -1. So that means, oh, okay, So negative 1 should go there, because if I start with 0 and I say, let's go ahead and subtract 1 from 0, that means I have to rotate the pointer counterclockwise 1 slot. That ends up pointing over here. So that means the bit pattern of 111 seems to make sense. It seems to make sense to use the binary bit pattern 111 to represent the value of negative 1. And obviously, now that we try to do this, we have a big, huge question. So if I just look at the bit pattern 111, is it representing 7 or is it representing negative 1? Okay, and the answer to that question is very interesting. Okay, and most people would say that, but Tech, you're not answering, you're evading the question. So the answer to that question, if somebody is to ask me, what is 111 representing? Is it representing 7 or representing negative 1? Here's my answer, and you probably want to remember it for a little bit of time too, is why do you care? Okay, it seems like I'm deflecting the question, but I'm not really deflecting the question. The real answer really is, why do you care? Okay, because the 111 may be representing 3 pixels on the screen that they're all lit, okay, or 3 dots, that you have to put inks or put a toner on, on the printout. So we have no idea of how to interpret 3 ones right next to each other, because that is just what it is. Okay, those are just 3 bits of 1. So inherently, it has no association to a particular value. It's just a bit pattern. Okay, the only time you need to know whether it's a 7 or a negative 1 is when you try to compare the value of that particular bit pattern to the value of another bit pattern. In other words, if you're not comparing, you don't need to know whether it's a 7 or a negative 1. Okay, so go ahead. So what we need to do now, I know the lecture time is over already. So what you need to do for the rest of today is to make sure that you understand the concepts of binary addition and binary subtraction. But now we are moving on to signed value representation, which means if you can read this module before tomorrow at 9 a.m., it'll be great. Okay, the lab is already open. Okay, Carry look ahead at part 1 is already open, and let me look up the passcode to it. The passcode is 3x3 part 1. So I'm going to write it in Discord. Okay, the passcode of the lab is 3x3 part 1, and I'll pin it so the people who are watching the recorded version can also quickly locate that. There we go. All right, cool. So what I'll do is I'm going to take a 10-minute break, and then I'll be back to answer questions about this lab. I'm going to close the live stream stuff now.